Hello everyone, and welcome to the rather long Central Force Post Lab. And this one's rather long because we have three independent variables to deal with, so three parts of the lab to build, and then we have to put the three parts together into one final math model. So, first third of the lab, you varied the mass, keeping the speed and radius constant, right? And then measured the resulting force, mass in kilograms, force in newtons. When you graph that, your graph should have been both linear and containing 0, 0, which means that force and mass are proportional. If you double the mass of the object moving in a circle at a constant speed, you need twice as much force to keep it doing that. If you have 3 times the mass, you need 3 times the force. Right? So just a direct proportion. If we make a y equals mx plus b math model out of this beautifully linearized graph, the y variable is, of course, the force. Right? The slope here, I'm going to throw in a theoretical slope, and as part of the process here, we'll figure out, why that is. Where did I get this 3 from? But hopefully that is pretty close to what you got. At least if you put it into the computer, into the Google form, it definitely is. Units, rise over run for slope. Units of rise are newtons. Units of run are kilograms. Now, those can be simplified. Okay, basically this slope right now means for every kilogram of mass, you got 3 additional newtons, or you needed 3 additional newtons of force. Every 1 kilogram of additional mass required 3 newtons of additional force. But we can reduce these, which often helps us see where they come from. Remember that a newton is a derived unit. It comes from F equals ma. It is the force required to make a 1 kilogram object accelerate at 1 meter per second squared. So a newton is a kilogram meter per second squared. The kilograms cancel, and we're left with units of meters per second squared. The x variable here is the mass, and the y-intercept is 0, which in this case means that when there's no mass, there's no force required to make it move in a circle. Of course not, because there wouldn't be an object. Now, if you take a little look at this, you might notice something here. The units on our slope are acceleration units. So this is force, mass times acceleration. That looks familiar. In this third of the lab where you varied the mass, you kept the radius constant at about 30 centimeters, 0.30 meters, and the speed constant at about 0.94 meters per second. Right? Give or take a little bit depending on how accurately you measured the period, right? But it had to be kind of in this range if you were going to end up with the right slope. Okay, so that's the first third of the lab. Second third, you varied the speed in meters per second and measured the resulting force in newtons, right, required to keep it moving at that speed in a circle. You kept the mass and the radius constant. When you graphed force as a function of speed, you didn't get a straight line. You got our old friend, the top opening parabola. Hopefully by now, when you see one of those, you say, oh, to linearize this, I need to square the x variable. So when you graphed force in newtons versus speed squared in, notice we have to square the units, meters squared per second squared, that gave you a linear graph that went through 0, 0. Since this graph was linear and went through 0, 0, what does that tell us? Well, that tells us that force and speed squared are proportional to one another. Not force and speed, that's a top opening parabola, but force and speed squared is linear and contains 0, 0. So if we want the object to go twice as fast, we don't need twice the force, we need 4 times the force. Right? If we want the object to go 3 times as fast, we don't need 3 times the force, we need 3 squared, 9 times the force. Right? So notice here that changing the speed has a bigger effect on the force required than changing the mass did. Right? Because mass was just direct proportion. This is speed squared. Now if we make a math model out of our linearized graph, right? Because this is the linear one, so y equals mx plus b, the y variable is again the force. And that's going to equal your slope. Now, theoretically, I believe your slope should be around 0.17, right? Which your slopes were around if you successfully entered it into the Google form. Why? We'll get there, right? As to why, how we could figure out that that was the slope, all right, or needed to be the slope in this case. Units, well, again, units come from rise over run. So the units of rise are newtons, and the units of run are meters squared per second squared. Now, that doesn't look like anything will simplify, but remember again, a newton is a kilogram meter per second squared. So notice the meter on top cancels out with one of the meters on bottom. The per second squareds on top cancel out with the per second squareds on bottom. And we are left with units of kilograms per meter. Now notice these are units of mass over units of radius. Interesting. So I'm going to put my reduced units on here, kilograms per meter. The x variable, right, is the speed squared, not the speed, that wasn't linear, right, but the speed squared. And the y-intercept was still 0, which means, as you might expect, that if there's no speed, it requires no force. If the object's just going to sit there, right, it doesn't need any force because it can't move, right? It'll just sit there. In this half of the lab where you varied the speed, you kept the mass constant at about 50 grams, 0.050 kilograms, and you kept the radius constant at, again, 0.30 meters. Those were choices we made inside of the pivot, right, if you followed the instructions. And these will be important when we finish up and put everything together. So this is the second third of the lab. Final third of the lab was where you varied the radius, which we measured in meters, I hope you converted, versus force in newtons. This one also was not linear. It looked more like that. What is that? Well, I hope you remember that that is a hyperbola. How do we go about linearizing a hyperbola? Well, let's look at what's going on here. As your radius got bigger, right, as your radius got bigger, your force required was smaller. It took less force for a bigger radius, right, than for a smaller radius. Now, what kind of relationship is it when one variable gets big, the other gets small? Yes, that is an inverse relationship. So, to linearize, we might want to try force in newtons versus the inverse of radius, 1 over the radius, in units of 1 over meters. Right? Invert the variable, you got to invert the units. And in fact, if you try that, that gave you a linear graph with essentially no y-intercept, which tells us that the force is proportional to 1 over the radius. Or you could use the magic word, and you could say force is inversely proportional to the radius. So it's either inversely proportional to the radius or proportional to 1 over the radius. Don't use inverse and 1 over in the same sentence, or it's like a double negative. It cancels itself out, right? So it's either inversely proportional to radius or proportional to 1 over the radius. We can create a math model for the linearized graph for this one. Of course, y equals mx plus b. As throughout the entire lab, the y variable is the force. That equals your slope, which for reasons which we will get to in just a few minutes, I think should be about 0.039, 0.04, all right, give or take a little bit. Units, well, again, rise over run, and we can simplify. The rise is in units of newtons. The run is 1 over meters. But remember, a newton is a kilogram meter per second squared. So how can we simplify this? Well, let's remember this horizontal line means divide by. So dividing by 1 over a meter is the same as multiplying by a meter over 1, right? Multiplying by the reciprocal. So if we multiply this times a meter, we get a kilogram meter squared per second squared. Well, that's a mess of units, right? But that's what they are. Where does that come from? A little hard to see right now, but we'll figure it out as we build our math model. The x variable is 1 over the radius, not radius, that's not linear, right? 1 over the radius. The y-intercept we need to be a little careful of. Remember, these inverse things have a couple of quirks, inverse relationships. It doesn't mean when the radius is 0, the force is 0, because look, that's not on the original graph, right? It's when 1 over the radius approaches 0 that the force approaches 0. But what kind of radius do we need to have to make 1 over the radius approach 0? A really, really big radius, right? 1 over a really, really big number is close to 0. So, little pre-calculus limiting idea here. What the y-intercept means is that as the radius approaches infinity, which is a really, really big number, the force approaches 0. Right? As the radius approaches infinity, the force approaches 0. And you can go the other way. As the radius approaches 0, the force approaches infinity that you would need. Right? So a little weird, little limiting thing that you've seen a couple other times here when we have this inverse relationship. In this third of the lab, where we varied the radius, we kept the mass constant at 100 grams, 0.100 kilograms, and we kept the speed constant at roughly 0.63 meters per second. Right, this is what I measured using the period that I measured in the pivot, but it's hopefully fairly close to what you had. So, at this point, we know 3 relationships. We know that the force is proportional to the mass, the force is proportional to the speed squared, and the force is inversely proportional to the radius. Well, you might remember when we've had these multivariable labs in the past, how do we shove them all together? Well, when they're all proportional to the same thing, force, force, and force, we put them together by multiplication. So that's mass times speed squared times 1 over the radius. Simplifying is mv squared over r. Now, as you can imagine, this will make a great concept builder. Okay? What happens if we double the mass? Well, the force doubles, right? But what happens if we double the mass and we double the radius? Well, nothing changes because 2 over 2 is 1. But what if we double everything? Well, then 2 over 2 is 1, but 2 squared is 4, so we'll need 4 times as much force. Kind of get the idea? Don't worry. You'll break these down and get some practice in this, right? But it allows us to change 1 to 3 of these independent variables and see what is going to happen to the force. But it's not as powerful as it could be, because it doesn't allow us to say this mass at this speed at this radius requires this much force. For that, we need an equation. And hopefully you remember that to turn a proportionality into an equation, you must multiply in a constant of proportionality, which I'm going to call z for now until we have a number to plug in there. Like, remember, pi is the constant of proportionality between the circumference and the diameter of a circle. Right? Circumference and diameter are proportional. Pi makes it an equation. So we need to figure out what this is. Right? What is z in this case? Is it something nice that we can forget? Does it have units? Right? Or is it something complex that we need to remember? Well, let's find out, because we now have, z is the constant of proportionality. We now have not 1, not 2, not 3, but 4 math models, right, that describe the motion of this object moving in a circle at a constant speed. The only problem is we don't know what this constant is. But perhaps we can tease it out if we compare our general math model with each one of these specific math models one at a time, right, and try to tease out what z is. So let me take this math model, and I'm going to rewrite it to look more like the one we got in the first half of the lab. In other words, I'm going to factor the m to the outside, okay? And then I get this. See what I did there? I mean, that's okay, right? These are multiplication and division, so they're commutative and associative. So I can change the order and the grouping. So if I pull this mass outside, right, then compare these 2 equations. If both of these equations are supposed to accurately describe what happened in this third of the lab, then the slope we got in the lab has to be equal to z times the speed squared over the radius. Do you see that? This part's got to be this. Well, in this part of the lab, we kept the speed and the radius constant. So what was the speed squared over the radius? Well, let's see. Right? Speed squared over the radius is 0.94 meters per second, which is squared over 0.30 meters. Let's check out the units. If we square the top, we get meters squared per second squared. and then the meter on the bottom cancels out with one of the meters on top, which means we are left with meters per second squared, which are the same units as our slope. And if you punch this into a calculator, 0.94 squared over 0.3 is basically, to 2 sig figs, 3.0. So v squared over r is already 3.0 meters per second squared. So hang on. See if you can catch this now. If z times v squared over r has to be 3 meters per second squared, and v squared over r is already 3 meters per second squared, then what does z have to be so that you can multiply it by v squared over r and get 3 meters per second squared? Not trying to be tricky. It just has to be 1, right? If z is 1, 1 times this is this, which is our slope. And it's 1 with no units, because v squared over r already had the right units with the slope. Well, this is wonderful, because 1 is the world's best constant, right? Because when you multiply by 1, it just disappears, and there's no units. Is this the same for the other two parts? Well, let's see. Let's compare our general math model to our math model we got in the second half of the lab. Notice all I did was pull the v squared outside. Then this slope has got to be equivalent to z times the mass over the radius. But in this third of the lab, we kept the mass and the radius constant. So what is the mass over the radius for this third of the lab, you ask? Well, notice the units work out to the same units as the slope, kilograms per meter. And 0.050 over 0.3 is, in fact, 0.17. So once again, if m over r is already the slope with the right units, z just needs to be 1. One more check. If we factor out the 1 over r, right, what we have left is z times m of v squared, and z times mv squared has got to be equal to this slope if both of these math models accurately describe what happened in the lab. Well, what is m times v squared? Well, in this third of the lab, we kept the mass and the speed constant. So sorry, I had to kind of move this over to make it fit. But mv squared is this. Let's check out units. Notice here, meters per second, which are squared, are meters squared per second squareds, times a kilogram is a kilogram meters squared per second squared. Oh, these slope units are mass times speed squared units. And if we multiply the numbers out and square the speed, we in fact, as you might expect at this point, get 0.039 kilogram meters per second squared, which is, of course, the slope, which means if you're going to multiply by a z, it just needs to be 1. So we appear to have pretty good confirmation that the general math model is true if our constant of proportionality is 1 with no units. Notice here, folks, this is how I decided what slope I would assume you were going to get, right? When I made the Google form, I went in here and I said, oh, okay, the slope's supposed to be speed squared over radius. So if this is my speed and this is my radius, our slope should be near 3. And so that's what I put in the Google form and said, well, you should be within about 5% above or below if, you know, with a nice pivot interactive to do. And then I looked at the second half of the lab and said, well, the slope's supposed to be mass over radius. And the third part of the lab and said, well, the slope's supposed to be mv squared. I hope you're starting to see here how math and modeling things and reality can go together to help us to create these math models which accurately describe the reality. So, if our constant proportionality is 1 with no units, that's the greatest constant ever, because when you multiply by 1, nothing happens. 1 is, of course, the multiplicative identity. And so if you plug a 1 in, we just get the equation. The equation that relates the speed required to make a certain mass object move in a circle at a constant speed, a circle of a certain radius, right? This is the mass of the object, this is the speed that it's moving in, this is the radius of the circle it's moving in, and this is how much force it requires, is just force equals mass times speed squared over the radius. This is a special equation that is only for situations like in our lab objects moving in a circle at constant speed. Objects that don't move in a circle or don't move at constant speeds can't use this equation, okay? This is specific to what we did in the lab. That's why we do the lab first, so that you know what the equation does, right? What kind of situation it applies to. Okay? And again, this is for an object moving in a circle at a constant speed. So yeah, we can change the variables, this doubles, that doubles, whatever, and figure out what happens. But now we can actually decide how much force do we need to make a certain mass move at a certain speed in a certain radius circle at a constant speed. All right? Now, this movement is important enough, and it's common enough, it's not super common, but it's common enough in the world, that it's given its special name. So if this is our mass moving in a circle at a constant speed, maybe we're looking down on it, right? I don't want a vertical circle yet. That gets a little more complex when gravity factors in. So let's assume we're looking down on this, right? This is what we call uniform circular motion. UCM for short. Uniform, remember, in physics means constant, right? Uniformly accelerated motion was constant acceleration. So this is motion in a circle at a constant speed. Uniform speed, if you will, right? So you may hear me say this all the time. All right, so here's an object moving in a circle at a constant speed, or I might just say here's an object moving in uniform circular motion, or UCM, if I want to, type it out in a worksheet or something, right? All of those mean the same thing. But here's a little question. Is this ball, which is moving in uniform circular motion, is it accelerating? Well, let's remember, acceleration is the rate of change of velocity. It's how quickly your velocity is changing. And I am being super specific with my language. Uniform circular motion says you're moving in a circle at a constant speed. Acceleration is how quickly your velocity is changing. Well, let's take a look at this object right about, here's the acceleration. Let's take a look at it right about here. Ready? There we go. Okay. This is part of the the IVV I hope you watched. Okay? But I want you to watch what the ball does. Where does the ball go when the force stops being applied? Okay, when the force stops being applied, where does the ball go? What direction does it go? Because that's the direction it was moving when the force stops, right? So here we go. Watch the movie. So here he's pushing in on the ball, and then he stops. Now it's hard to tell from there, but look up here. Ooh, do you see that? So the ball was down at the bottom and moved off straight to the right. Right? If you've done the pivot, you know that means that the velocity of the ball then would be here, right? Straight to the right. And if we drop in a radius, notice there's a 90-degree angle. When something's at a 90-degree angle to the radius of a circle, what do you call that? You call that tangent. So the velocity here is tangent to the circle. And that's why it's sometimes known as the tangential velocity. Remember that word that was in the pivot, right? And I said, well, I'll explain what that means later, okay? They called it the tangential speed. I would have preferred velocity, but okay. They called it the tangential speed because that's the direction. It's always tangent to the circle. If you release this ball, if I let go of the string here, it's going to go off tangent to the circle. Notice, not straight out, not straight in, not continuing along the circle. Because an object has inertia, it has a tendency to continue moving whatever direction it was moving before. So once the force isn't applied, it just moves off inertially. It moves off tangent to the circle. Well, watch what happens if we put this in motion. Watch what happens to that velocity arrow. And I'm just leaving behind some at various points, right? Look at that velocity arrow. Are those velocity arrows identical in every way? Well, they're certainly the same size. because we've been saying all along it's a constant speed, right? That's how long the arrow is. But are all these arrows exactly the same? Well, of course not. While they're the same size, aren't they pointing in different directions? This one's pointing to the right. This one's pointing down. This one's pointing to the left. This one's pointing up. This one is constantly changing direction. And so if it's constantly changing direction, it is constantly changing its velocity. And if it's changing its velocity, it is accelerating. Okay? So we haven't talked a lot about this. It's come up here and there. Like, for example, at the highest point on a projectile, right, where its speed is 0, but it's changing from going up to coming down, we were saying, yes, it's accelerating. Well, this one is accelerating at every point because it's constantly changing direction, therefore velocity. It's not changing speed, it's changing velocity. This is where the pickiness of our language all year long is important, right? Because saying something has a constant speed, right, is definitely different than saying something has a constant velocity. Something with a constant velocity goes in a straight line at a constant speed, right? So, yes, this object is accelerating. So then the question becomes, well, we have a formula to calculate the force required. Can we make a math model to calculate the acceleration that it has? Well, yeah, right? At least the magnitude of it. If this is the force required, we already know an equation for the force required to make something accelerate. That's what we call Newton's second law. Right? So if I rewrite this equation, right, pull the m out over here, we can compare it to Newton's second law. Newton's second law says net force equals mass times acceleration. So if you compare these two equations, do you see what the acceleration has to be? Yeah, it has to be the speed squared over the radius. And this again is for an object moving in a circle at a constant speed. So this is a special acceleration. And we're going to give this special force and this special acceleration a name. We'll do that in the next discussion, all right, next video. But for now, recognize that it's a special acceleration, okay? It only is the speed squared over the radius if it's moving in uniform circular motion, moving in a circle at a constant speed. But this now makes it a given. Kind of like when we were doing projectile motion problems, we automatically knew if we were near the surface of the Earth that our acceleration was negative 9.8 meters per second squared, so we could just use that. Well, now, if we have something moving in uniform circular motion, moving in a circle at a constant speed, we know a way to calculate the acceleration, and it's only one equation. We don't need 4 kinematic equations for this. We just need one. And all it is speed squared over radius, and boom, you know your acceleration. And if you know your acceleration, you can calculate the force as long as you know the mass. So notice this mv squared over r is really mass times acceleration, where the acceleration is the speed squared over the radius. Whew. That's a lot of information about why objects move in uniform circular motion and kind of how we can describe that motion.